We learnt earlier about different physical quantities, of which 7 are considered fundamental according to the SI system of measurements, while the others are derived physical quantities. The 7 fundamental quantities are length, mass, time, electric current, thermodynamic temperature, amount of substance, and luminous intensity. These are also referred to as base quantities. All other physical quantities can be conveniently derived from these base quantities. Thus, we have relationships between fundamental quantities and derived quantities. Therefore, when a derived quantity is expressed in terms of base quantities, the resultant expression is the product of different powers of the base quantities. For example, consider the quantity force. Force is product of mass and acceleration. Mass is a base quantity, and acceleration is the derived quantity, which is the ratio of change in velocity to time. Velocity, which is also a derived quantity, is the ratio of displacement to time. Displacement, in basic terms, is length. Thus, velocity can be expressed as the ratio of length to time. Using the same logic, we can write acceleration as length by time divided by time. Thus, the expression for a quantity force can be simplified as shown. From the expression, it is clear that the exponents of mass, length, and time in the expression for force are 1, 1, and -2 respectively. These exponents of base quantities in the expression for force are called dimensions. Thus, the dimensions of a physical quantity are the powers or the exponents to which the base quantities are raised to represent that quantity. We say the dimensions of force are 1 in mass, 1 in length, and -2 in time. For convenience, we use symbols to represent base quantities as follows. For mass, we use m. Length is denoted by L, and time by T. The other 4 base quantities are represented by symbols of their SI units, namely electric current by I, thermodynamic temperature by K, amount of substance by mole, and luminous intensity by CD. The physical quantity expressed in terms of its base quantities is enclosed in square brackets to show that it is an equation among the dimensions of the quantity and not among the magnitudes. Thus we can write the expression for force as force is equal to mLT power -2 as shown. Such an expression for a physical quantity in terms of its base quantities is called its dimensional formula. An equation which equates the quantity with its dimensional formula, is called a dimensional equation. Of the 7 base quantities in the SI system, we see that only 3, namely mass, length and time, exist in the dimensional formula for force. Thus, we can say that the dimensions of all the other 4 base quantities in the expression for force are equal to 0. In mechanics, most derived quantities are related to only the 3 base quantities of the 7, namely mass, length and time. Let us look at another example. Let us find the dimensional formula for pressure, which is equal to force per unit area. Area is the product of length and breadth. Length and breadth represent the base quantity, length. Thus, area can be expressed as length square, and hence its dimensional formula is L power 2. We know that the dimensional formula of force is mLT power minus 2. Now, the dimensional formula of pressure is obtained as shown. Following the same methodology, we find the dimensional formula for the volume of a body. Volume is the product of length, breadth and height. Height also represents the base quantity, length. Thus, the dimensional formula of volume is L power 3. Similarly, we can find the dimensional formula of mass density, which is the ratio of mass to volume. The dimensional formula for density is mL power minus 3. So far, we have discussed derived physical quantities, namely force, pressure, and density. These quantities have units, namely Newton, Pascal, and kilogram per meter cube, respectively. But there are certain derived physical quantities that do not have units. For example, relative density is the ratio of the density of a substance to the density of water. As it is the ratio of 2 identical quantities, it does not have any unit. Therefore, the quantity relative density does not have any dimensional formula. Another example is absolute refractive index, mu, of an optical medium, which is the ratio of the speed of light in air or a vacuum to the velocity of light in the given medium. Refractive index is just a number and is significant even though it does not have any unit, because the value of mu of a medium indicates the extent to which a ray of light bends on entering the medium at a given angle of incidence. Refractive index of a given medium is constant and does not have any dimensional formula. You will learn about refractive index in detail later in the course. We also have certain physical constants, each of which has a unit as well as dimensional formula. For example, the universal gravitational constant G is a constant whose value is 6.67 into 10 power minus 11 Newton meter square per kg square and is denoted by the expression G is equal to force F into distance d square by mass m square. Thus, the dimensional formula of G is obtained as shown. We obtain the dimensional formula of G as m power minus 1 L power 3 T power minus 2. You will learn about G in detail later in the course. So far, we have discussed physical quantities, which are expressed as the product of base or other derived quantities. We also learnt that a dimensional equation is the equation among the dimensions of the quantity and not among the magnitudes. But we may encounter situations where we need to add or subtract different terms involving base quantities. It is very important to know that when we write L plus L, as shown, we mean length added to length. So, we get length. Again, it is not 2 times L as we are not adding the magnitudes of the length. Similarly, if velocity is subtracted from velocity, we get velocity. Thus, Lt power minus 1 minus Lt power minus 1 equals Lt power minus 1. The table shows the list of some of the physical quantities and their dimensional formulae. You will learn about the applications of dimensional formula later in the course. We learnt earlier about the dimensions of some physical quantities. The dimensions of a physical quantity are the powers or the exponents to which the base quantities are raised to represent that quantity. An expression for a physical quantity in terms of its base quantities is called the dimensional formula. An equation which equates the quantity with its dimensional formula is called the dimensional equation. We will now learn about the uses of these dimensional formulae and dimensional equations. We know that a dimensional equation is the equation among the dimensions of a quantity and not among the magnitudes. Thus, when we write L plus L, as shown, we mean length added to length. So, we get length again. It is not 2 times L as we are not adding the magnitudes of the length. This property of a dimensional equation can be used to check the dimensional consistency of equations by analyzing the dimensional formula of quantities on both sides of the equation. For example, consider the motion of a body moving with an initial velocity u and uniform acceleration a, having made a displacement s in a time interval t. The motion of the body can be represented by the equation s is equal to ut plus half at square. Let us now verify the consistency of this equation using dimensional analysis. On the left-hand side of the equation, we have displacement S. This is basically length and its dimensional formula is L. On the right-hand side of the equation, we have two terms, each involving the product of two different quantities. The first is UT and the second is half AT square. When the magnitudes of two or more physical quantities are multiplied, their dimensions are also treated in the same manner as done with ordinary algebraic symbols. In this case, in the first term, it is the product of velocity and time. The product of the dimensions of these quantities is Lt power minus 1 into t, as shown. On simplification, we get L. The second term on the right-hand side of the equation is half AT square. Half is a constant and thus does not have any dimensions. In the first term, it is the product of acceleration and time square. The dimensions of A are Lt power minus 2 and that of t are t. Thus, the dimensions of AT square are as shown. Taking the dimensional formula of the physical quantities in both the terms on the right-hand side of the equation, substituting their corresponding dimensions and simplifying, we find it is equal to L, which is the dimension of length as obtained on the left-hand side of the equation. Thus, the dimensions of the quantities on both sides of a given equation are the same. This proves that the equation is correct. It is very important to note that physical quantities represented by symbols on both sides of a mathematical equation must have the same dimensions. This principle is called the principle of homogeneity of dimensions and is useful in checking the accuracy of an equation. This principle can also be used to derive expressions for physical quantities if the other quantities on which it depends are mentioned. For example, we can derive an expression for the time period of a simple pendulum, assuming that its time period t depends on the length, mass of the pendulum, and the acceleration due to gravity at a given place. Let us take the constant of proportionality k as 2 pi. We assume that the time period is proportional to L power A, M power B, and G power C, where A, B, and C are constants. Replacing the proportionality symbol, we get a constant k. Hence, the time period is equal to k into L power A, M power B, G power C. We now need to find the values of A and B using dimensions of the physical quantities on both sides of the equation. The dimensional formula for time is T. The dimensional formula for length is L. The dimensional formula for mass is M. The dimensional formula for acceleration due to gravity is Lt power minus 2. The constant does not have any dimensions. Hence, the dimensional formula of the quantities on the right side of the equation is simplified as shown. Let this be equation 1. The dimensional formula of the quantity on the left side of the equation is as shown. As we do not have the term for M and L on the left-hand side of the equation, we take their powers to be 0 as shown. Let this be equation 2. Equating Equations 1 and 2. We compare the powers of the base quantities on both sides of the equation. Thus, we get b equal to 0, a plus c equal to 0, and minus 2c equal to 1. On simplification, we get the values of b equal to 0, c equal to minus half, and a equal to plus half. Thus, the expression for the time period of the simple pendulum becomes 2 pi into the square root of L by G as shown. The value of k, which is equal to 2 pi, cannot be found by using dimensional analysis. However, this method cannot be applied to derive equations where addition or subtraction of different terms is involved. For example, we cannot derive the equation S is equal to ut plus half at square using dimensional analysis, even though we checked its dimensional consistency. Dimensional equations can be used to convert units of a given physical quantity from one system to another, and to thus find the conversion factor. For example, consider the physical quantity force. The dimensional formula of force is mLT power minus 2. The SI system of unit of force is Newton, and its CGS unit is dyne. Hence, 1 Newton is equal to 1 kilogram into 1 meter into 1 second power minus 2. Similarly, 1 dyne is equal to 1 gram into 1 centimeter into 1 second power minus 2. Now, we divide 1 Newton by 1 dyne and then find the ratio of Newton to dyne as shown. Thus, 10 power 5 is the conversion factor to convert Newton to dyne. Dimensions are generally used as a basic test to check the consistency of an equation, where there is a doubt regarding its correctness. However, this test cannot be completely relied upon, especially in the case of dimensionless quantities or functions. Dimensionless constants cannot be obtained by this method. For example, the arguments of some dimensionless functions such as trigonometric, logarithmic, and exponential functions cannot be obtained using dimensional analysis. The ratio of similar quantities results in a pure number, which is again dimensionless. For example, angle is the ratio of arc length to radius, which is length divided by length. Absolute refractive index of a medium is the ratio of the speed of light in a vacuum to that in a given medium, which is the ratio of speed to speed. The test of consistency of dimensions not only tells us the consistency of units, but also helps the user ignore the units to be mentioned and conversions among multiples and submultiples of units. If an equation is put to the consistency test using dimensional analysis, and if the equation fails, it means that the equation is proved incorrect. If the equation passes the consistency test, it does not mean that the equation is correct. Thus, an equation proved to be dimensionally correct need not be an exact equation, but an equation that is proved to be wrong dimensionally must be a wrong equation. The dimensional analysis method is very useful in drawing relationships between various interdependent physical quantities. This analysis can only test dimensional validity, but not the exact relationship between the physical quantities in any given equation. The dimensional method cannot differentiate between physical quantities which have the same dimensions. For example, even though the quantities energy and torque have the same dimensions, they are completely different in every sense.